Natural convection type condensers. In the natural convection type, heat transfer from the condenser is by buoyancy, which induces natural convection and radiation. These condensers are used for little capacity refrigeration systems like household refrigerators and freezers. The natural convection type condensers are either plate surface type or fin tube type. Plate surface type condensers are utilized in small refrigerators and freezers. The refrigerant carrying tubes are attached to the outer walls of the refrigerator. The whole body of the refrigerator, except the door, acts sort of a fin. Insulation is provided between the outer cover that acts like a fin and therefore the inner plastic cover of the refrigerator. It is for this reason that the outer body of the refrigerator is usually warm. Since the surface is warm, the problem of moisture condensation on the walls of the refrigerator doesn't arise in these systems. These condensers are sometimes also called flat-back condensers. Forced convection type condensers. In forced convection type condensers, the circulation of air over the condenser surface is maintained by employing a fan or a blower. These condensers normally use fins on the air side for good heat transfer. The fins are often either plate type or annular type. Forced convection type condensers are commonly used in window air conditioners, water coolers, and packaged air conditioning plants. These are either chassis-mounted type or remote-mounted type. Chassis-mounted type. In chassis-mounted type, the compressor, induction motor, condenser with condenser fan, accumulator, HP or LP cutout switch, and pressure gauges are mounted on one chassis. Remote-mounted type. The remote-mounted type is either vertical or roof-mounted horizontal type. Typically the air velocity varies between 2 meters per second to 3 meters per second. Double pipe or tube-in-tube type condenser. Double pipe condensers are normally spent to 10 TR capacity. In these condensers, the cold water flows through the tube, while the refrigerant flows through the annulus and counterflow. Headers are used at both ends to form the length of the condenser small and reduce pressure drop. The refrigerant within the annulus rejects a neighborhood of its heat to the surroundings by free convection and radiation. The warmth transfer coefficient is typically low because of poor liquid refrigerant drainage if the tubes are long. Shell and coil type condenser. These condensers are utilized in systems up to 50 TR capacity. The water flows through multiple coils, which can have fins to extend the warmth transfer coefficient. The refrigerant flows through the shell. In smaller capacity condensers, the refrigerant flows through coils while water flows through the shell. When water flows through the coils, cleaning is completed by circulating suitable chemicals through the coils. Shell and tube type condenser. This is the foremost common sort of condenser utilized in systems from 2 TR up to thousands of TR capacity. In these condensers, the refrigerant flows through the shell while water flows through the tubes in single to 4 passes. The condensed refrigerant collects at the bottom of the shell. The coldest water contacts the liquid refrigerant in order that some subcooling also can be obtained. The liquid refrigerant is drained from rock bottom to the receiver. There could be a vent connecting the receiver to the condenser for smooth drainage of liquid refrigerant. The shell also acts as a receiver. Further, the refrigerant also rejects heat to the environment from the shell. Evaporative condensers. In evaporative condensers, both air and water are taken to extract heat from the condensing refrigerant. Evaporative condensers combine the features of a cooling system and a water-cooled condenser during a single unit. In these condensers, the water is sprayed from the top part on a bank of tubes carrying the refrigerant, and the air is induced upwards. There is a skinny water film around the condenser tubes from which evaporative cooling takes place. The warmth transfer coefficient for evaporative cooling is extremely large. Hence, the cooling system is often operated at low condensing temperatures, about 11 to 13,000 above the wet bulb temperature of the air. The water spray counter current to the airflow acts as the cooling system. The role of air is primarily to extend the speed of evaporation of water. The required airflow rates are within the range of 350 to 500 meter cube per hour per TR of refrigeration capacity. This is it for today's video. Let us know in the comment section which topic you want to see next. Before leaving, check the exclusive offers, link in the description below. And do not forget to hit the like and subscribe button. To find out more on the subject, continue watching the next video.